Assalamu alaikum students. So today we are going to compare our energy equation with the Bernoulli equation. Why we are doing this comparison? Because Bernoulli equation and energy equation both are dealing with the conservation of energy. And as you know, whenever we talk about energy, so there is no such device up till now that converts the total available energy into useful work. So what we will have is some losses. So the purpose of comparing our energy equation with the Bernoulli equation is to find out the terms that will explain our losses inside the system, that is our fluid. So previously we derived this equation for a simple streamlined tube, as you remember from your previous lecture, that had one inlet, one outlet, and for that we wrote an energy equation that looked like this. So these are the uh, terms for change in internal energy, change in the pressure at the inlet and outlet, change in velocity at the inlet and outlet, and the change in the potential energy at the inlet and outlet multiplied by the mass flow rate, and these terms are equated to the net flow in, that is the heat transfer, net rate of heat transfer in to the system, and the net rate of work transfer into the system. And this whole term, this was the integral for the control surface. This control surface integral was applied to an inlet and outlet, one inlet and one outlet situation. So we got this equation. So now what we are going to do is to first divide both sides of these equation by mass flow rate. By doing so, we will get rid of the mass flow rate on the left hand side. If we divide this by m dot, divide this by m dot, and divide this by m dot. So what we are going to get on the right hand side is the specific rate of heat transfer in and the specific rate of the work transfer. So let's see what these terms will be. These will be the terms that we will get. These are the this is the term for the specific rate of heat transfer, and that is the work transfer to the shaft. So now what will happen to the left hand side if we write a Bernoulli equation for it? As you remember, this was our Bernoulli equation. This is our Bernoulli equation that we derived for along the streamline. That is the Bernoulli equation along the streamline. That is the pressure term, that is the kinetic energy, that is the potential energy. You can see these terms in the energy equation as well. This is the pressure term, this is the velocity term, and this is the term for the potential energy. So let's write this energy equation just in terms of these and equate it. So this is how my energy equation will look like if I write it in terms of the terms that are represented here in the Bernoulli equation. So these are my pressure terms, the velocity term, the potential energy at the outlet, and the same terms at the inlet. And these two terms that I am going to get is the change in the internal energy at the outlet and the inlet. I have transferred these terms to the right hand side of this equation, and this is the specific rate of heat transfer in plus the work that is done on the shaft. So this is how my energy equation will now look like. To simplify it a bit further, what we are going to do is to divide this by gravitational acceleration. Why we are dividing this by gravitational acceleration? When we divide all these terms by gravitational acceleration, what we are going to get is we are going to get the units of each of these terms in lengths. Like if I divide this by g, so what I am going to get is a unit that will be in terms of length, that will be representing length. Same is for this. If I divide this by g, I will get a unit for this term that will be length, and if you divide this by g, you will get, as you can see, a unit that is length, and same goes for these two. And these will be, these terms will represent my losses, which I will discuss in a little while. So let's divide this equation by g and see how this equation behaves. So this is what we get when we divide our equation by gravitational acceleration, so that we can get the units of each of these terms in terms of length. So all of these terms have units now in length. So this is what we are going to get. Rho g is equal to gamma. You remember that this is the specific weight. This is again at the inlet, that was at the outlet. So these are the terms we are going to get after dividing this equation by gravitational acceleration. So what are these? All these terms in this equation have units of length. They are called heads. As you remember, when we were discussing manometers, we said that we can also represent pressure as millimeter of mercury. So pressure is also a form of energy. So we can, if we can represent pressure as in terms of length, so why not the other terms? So this is what we are doing here. We are representing these different energies in terms of heads now, and head is a graphical way of representing energy. If you remember your hydraulic and your energy grade lines, so we can represent energy in terms of heads also. So now moving on to the next slide, and let's see what the losses will be also, and let's see what different type of heads we have in this equation. So this is the equation that we got from the previous slide. Now these are the different types of heads that we have in this equation. This is the pressure head, this is the velocity head, and this is the elevation head. And this is again the pressure head at the outlet, the velocity head at the outlet, and the elevation head at the outlet is equal to the pressure head at the inlet, the velocity head at the inlet, and the elevation head at the inlet. These terms now represent the losses, or the energy added to the fluid in this case, or extracted from the fluid. Again in this case we will discuss it in a little while. So let's now discuss these losses, or what these terms represent. And okay, so these three terms represent the total mechanical energy in the fluid. These three terms, the pressure head, the velocity head, the elevation head, if we add them up, what they represent is the total mechanical energy that is available in our fluid that we can utilize. But we cannot utilize the total mechanical energy. Some of that will be lost, some of that will be lost because of the second law of thermodynamics, because we cannot utilize the total energy into useful work. That is impossible because of the losses. So let's see what these losses will be in this case. So what this term is representing in my equation is that is this term. This term here represents losses. These are called the head losses, and this is the loss of mechanical energy due to viscous effect in the pipes and fittings. And this will always be greater than 1 if our fluid is viscous. So we had a discussion on viscosity, and we said that viscosity is what the fluid particle are. Again, if we define viscosity, that why does viscosity occur? If there are 3 layers of fluid, and in the first layer the fluid are moving a bit faster than in the second layer, and in the third layer they are even more slow. So due to this different velocities in these layers, what happens is if a particle goes into this layer of a particle of high momentum goes into the layer of low momentum, so what will happen? It will lose energy. And if a low momentum particle goes into the high momentum stream, then it will gain energy. So due to these interaction, what happens is friction happens, and due to this friction losses occur, and due to these losses we say that these are the viscous losses that are occurring inside the fluid due to the viscous effects inside the fluid. And these viscous effects are represented as head losses, and these are the loss of mechanical energy due to viscous effects in the pipes and fittings. So this is our first term for the loss in mechanical energy inside the fluid. So this term represents the loss. Now the next term is the work on the shaft work head, this term. If you are this term, that is the shaft work head. So gain or loss in mechanical energy due to shaft work. What does this mean, gain or loss? Remember that we are talking about a system, and system is our fluid, and this gain and loss of mechanical energy is in the fluid, that either the fluid is gaining mechanical energy or it is losing mechanical energy. So there are two cases when we talk about shaft work. So one is the pump. In the pump, the fluids gain mechanical energy because the shaft is working on the fluid. It is transferring energy to the fluid. So what happens is the mechanical energy is gained in this case of the fluid. The fluid mechanical energy is increased in this case. The other case will be, as we discussed previously, will be that of a turbine. In turbine, what happens is the fluid is working on the shaft. So the fluid is losing energy to transfer that energy to the shaft through impellers or buckets or whatever, and generate some electricity. So in case of turbines, the fluid is losing energy. In case of pumps, the fluid is gaining energy. So the shaft or work head can be the gain in mechanical energy or the loss in mechanical energy, depending on what situation are we working on. Either we are working on a pump or either we are working on a generator. So in that case, we will represent this shaft work head as a positive or negative sign that we have done previously in the previous lecture. So now let's put these terms into our equation and make some more sense out of our equation. So this is what happens. This is the shaft work head, and if I again divide this shaft work head by G, and similarly if I want to represent this in terms of rate of work transfer in terms of power, I can divide this by m dot, and that m dot is again equal to rho VA. So that is the positive work that the pumps does on the fluid, and that is the negative work that is transferred from the fluid to the shaft. So that's how we are going to represent these two work heads of the shaft. That one is the positive work head, that is the negative work head, representing that of the turbine, and that is of the pump. So these are the terms used for it. That is HP is the shaft work head of the pump, and that is minus HT is the shaft work head of the turbine. This negative sign represents the loss in mechanical energy, and here is a positive sign that you are not seeing, that is the gain in mechanical energy due to shaft work. So pump head is gain in mechanical energy due to pump, that is HP, and turbine head is the loss of mechanical energy due to turbines. This is how my final energy equation, if I take one inlet and one outlet, will look like. These terms at the outlet and the inlet represent the pressure head, velocity head, and elevation head. These are the total mechanical energy available at the outlet and the inlet, minus the head losses due to the viscous effects, plus the gain in mechanical energy due to pumps. If you are dealing with pumps, then there will be a gain in mechanical energy, but if you are dealing with a turbine, then there will be a loss in mechanical energy. So we need a single term, and what we do is we write this equation, and now we have a single term for this HP minus HT. So if you are dealing with pumps, so this HS will be positive. If you are dealing with turbines, this HS will be negative. So now we are representing this shaft work head by HS, and this HL is again the head loss due to the viscous effects in the pipes and fittings, and this is the energy that the fluid is losing due to friction inside the fluid due to the viscous effects. So this is what we did. We compared our energy equation with the Bernoulli equation for the purpose to define terms that are related to our losses inside the fluid, and these are the terms we are getting. These are the head losses and these are the gain or loss due to shaft work head, depending if you are working on the pump or depending if you are working with a turbine. So this is the final energy equation for a simple for a simple steam tube that we defined in the previous lecture for one inlet and one outlet. This is what our energy equation will look like, and these are the terms that we are representing the losses with. So let's look at this example 5.24 from your Munson book. So an axial ventilating fan, exhaust fan as we normally know it, driven by a motor that delivers 0.4 kilowatt of power. So this is the power of the motor to the fan blades produce a 0.6 meter diameter axial stream of air having a speed of 12 meter per second. So let's look at the diagram. This is a ventilating fan, so this is actually sucking some air out of a room. So this is the diameter 0.6 meter that they are talking about in the statement, and the velocity downstream, that is 12 meter per second. The flow upstream of the fan involves negligible speed. So this is the upstream of this fan, and at upstream the flow velocity is negligible. Let's suppose that the flow here was static and this exhaust fan was turned on to suck some air out of this room. So here at section 1 our velocity is 0. What we are going to do is to determine how much work of the work to the air actually produces useful effects. Remember we talked about pump in our previous slide, and we defined pump as a device that is actually adding energy to our fluid. So this is what this fan is doing right now. It is adding energy to the air. So this fan is moving and it is exhausting some air out. So actually it is adding some energy to the fluid, and what we are going to do is to find the actual work that this fan is doing on the air. So at the end we can estimate the fluid mechanical efficiency. So the actual work will include the losses. So we are going to find the actual work that includes the losses, and we will divide it by the ideal work that this fan is doing. So in that case we will get our mechanical efficiency. So let's see our governing equation for this case. This is our governing equation that we derived by comparing our energy and our Bernoulli equation. Now let's write some gravitational acceleration in the denominators. We can write gamma as rho g, 2g, and multiply and divide the elevation term by gravitational acceleration. I'm doing this because they are using this equation in this example. So just to be clear about the terms that they are using, I'm writing my equation as such. This is the head loss HL, and this is the shaft head that is available. So let's look at the solution and just make some sense out of this equation. So they have fixed this control volume. As you can see, the dashed blue dashes, this is the control volume for this particular example. Okay, and let's look at the equation now. So this is the work that the shaft will do on this air. So this is positive because energy is being added to the fluid. So this is the work of the shaft that is being done on the that is going to do some work on the fluid. This is my losses. These are my losses. So this is the loss here. This is the loss and the minus term. What they have done is they have shift the pressure at point 1, velocity at point 1, and the potential energy at point 1 to the left hand side of this equation, and this is what we get. They have multiplied this terms by gravitational acceleration. this whole term is multiplied by gravitational acceleration, and this term again is also multiplied by gravitational acceleration. So the equation they are using in the example, now you can make a little bit sense that what they are using. Okay, if you multiplied this left hand side of this equation by gravitational acceleration and multiply this right hand side by the gravitational acceleration, so this is what you get in return, this equation for the inlet and the outlet in this particular case. So now you can make some sense out of this equation, and now let's see the different terms that they are cancelling out and equating it to 0. So the pressure at point 1 and point 2 at my section 1 and section 2 will be 0 because we are dealing with atmospheric pressure. So at both these points, at point 1, at section 1 and at section 2, my pressure will be equal to pressure at the atmosphere. So these terms, the pressure terms will cancel out. This term will cancel out to 0 and this term will cancel out to 0. Then in the statement they are telling us that at the upstream the velocity is also 0. So V1 is also 0. So this term will also be equated to 0. There is no change in energy due to the elevation, means that there is no change in elevation in this particular case because air is entering at section 1 and exiting at section out. So no change in energy due to elevation is occurring. So we will cancel our elevation heads. These are these two terms, elevation heads, these two terms. We will cancel them out also here. So what we are left with is this term, that is V2 square by 2. So we know the velocity at the exit, V2 square by 2. So what we can do is we can find this term, that is the work done by the shaft on the fluid including the losses. So this is the actual work that is being done on the fluid in this particular case. So we will find the work by putting the values of V2 square by 2, and what we will get is this. So this is the work including the losses. This is the actual work including the losses. So this is the actual work this fan is doing on the air to exhaust it out. So now what we will need to do is to divide it by the ideal work. The ideal work that this pump, this exhaust fan will do on this air to vent it out, and what the ideal work will be, the one without the losses. So let's see how will we find the ideal work to find our efficiency. Let's move on to the next slide. So this is what our equation for efficiency will look like. This is the actual work that I defined in the previous slide. This is the actual work including the losses, and the one will be without the losses will be my ideal work that does not include any losses. So the ratio of these two will give me my efficiency. Now I know the value of these terms from the previous slide. I know the value of these terms, but I don't know the ideal work of this shaft that is transferred to the air. So I need to find this, and I need to recall some terms that I used in deriving the equation including the losses. So this is what the shaft work is equal to, that is the rate of doing work per unit mass. This is power per unit mass flow rate. So power per unit per mass flow rate gives us our work. So I know the shaft power from my statement, that is 0.4 kilowatt. What I need to do is to find the mass flow rate in this particular case, and my mass flow rate will be equal to these terms. So my m dot is rho AV, and I know the velocity at the exit V2 because at inlet V1 is equal to 0. So I am going to find the mass flow rate at the exit, and I know the diameter of the stream at the exit, so I can find the area by using pi by 4d square. The velocity, the density of the air can be put by as a standard value, that is 1.23 kilogram per meter cube, the density for standard air. So now I am able to find the work, that is the ideal work that the shaft is doing on the air. That does not include any losses. So this is the power of the shaft. So the shaft power was 0.4 kilowatt, and to include this kilo, exclude this symbol from our units, we will multiply this by 1000 and then divided by mass flow rate. These are these terms. So what I will get is the ideal power of my fan. So then this is what is the value of my ideal work. Now what will I do? I will find the efficiency using this formula. So by using this formula, what I am doing is the actual work, taking the ratio of the actual work that is being done by the fan and dividing it by the ideal work. So I get an efficiency of 75%. So the 25% are the losses. So in the comments they had made, they say that note that only 75% of the power that was delivered to the air resulted in useful effects, and thus 25% of the shaft power is lost to air friction, because we only considered the losses due to the fluid friction. So this 25% of the loss is due to the result in the air friction. So this is what our efficiency in this case will be. So hope this was clear. So let's look at this problem. Water flows through a valve in this figure shown. This is the figure at the rate of 1000 pound mass per second. So this is the mass flow rate. M dot is equal to 1000 pound mass per second. The pressure just upstream of the valve is 90 psi pound per square inch, and the pressure drop across the valve is 50 psi. So here at the upstream, P1 is equal to 90 pound per square inch. This is the pressure here, and then the pressure drops at the as 50 psi when it flows across this valve. So P2 will be 40 psi because the pressure drops 50 psi when it passes through that valve. The inside diameter of the valve inlet is 12 inches. This is the inside diameter at the inlet of the valve, and at the exit is 24 inches. If the flow through the valve occurs in a horizontal plane, determine the loss in available energy across the valve. So what we are going to do is to find the loss in the available energy across the valve. So let's look at this equation and just cancel out some terms. The first terms that we are going to cancel out are these elevation heads, because no such change in energy will occur due to the elevation, because elevation is nearly negligible in this case. What we are going to do is to also cancel out the losses due to the shaft. So the shaft head loss, that is the work of the shaft by the fluid or on the fluid. Here inside of this valve, no such mechanical rotor is present. So what we are going to do is to we are going to do the neglect this shaft head work, that is this term. So we will also equate this to 0. Remember when we were deriving the energy equation, so we also said that if there is no rotational part involved inside our control volume, so we will equate this work done by the shaft or work done on the shaft equal to 0. So here this is the shaft work head. So here inside this control volume, there is no such mechanical rotation occurring. So we will equate this term to 0. Remember that this will be our control volume. This whole inside inside of the valve will be my control volume. So inside this control volume, no such mechanical work is being done on this water. So now neither the water is doing work on this some component, mechanical component inside this valve. So this term will be equated to 0. Now the only losses that we are considering are the losses that these are the head losses due to viscous effects. So these are the only losses that we will consider in our equation. So now this is my governing equation for this problem. I am going to rearrange it for the losses that we are going to find, and let's see what our equation will look like. So now our equation will be HL, these are the head losses, P1 over gamma plus V1 square divided by 2G and minus P2 over gamma and minus P2 square divided by 2G. To cancel out the terms, that is the rho g term here, the gravitational acceleration term here, and rho g term here, we multiply both sides of this equation by g, and we know that our HL is equal to u naught minus ui minus net rate of heat transfer in divided by g is equal to P1 divided by rho g plus V1 square divided by 2g minus P2 divided by rho g and minus V2 square divided by 2g. So to cancel out these terms, my gravitational acceleration, I am going to multiply both these equations by gravitational acceleration. So this is what my equation will now look like. I will represent this term as my loss, and I'm going to write the final equation like this. So my loss in energy is equal to P1 over gamma minus P2 over rho, sorry, this is not gamma, this is rho, plus V1 square divided by 2 minus V2 square divided by 2. So this is my final equation, and now I'm going to find the values that I'm missing. So what I'm missing in this equation is the value of V1 and V2, and I can find that value with the help of this mass flow rate. If for m dot is equal to rho a v, so for velocity v1 I am going to put v1 a1. I can find the area at inlet. This is my section 1, this is my section 1, this is my section 2. So at section 1 I can find the velocity v1 by using this formula. I can put the value of the area as pi by 4 d1 square, and density of water, the standard value of density of water, and the mass flow rate is already known to be 1000 pound mass per second. So I can find v1 from this equation, from the same equation, by putting a2 and v2 I can find my v2. So using these equations I can find my velocity v1 and velocity v2. Because all the areas are known to me, I can find the areas by using the diameters by pi by 4 d square formula, and I will use the standard density of water that is in the English units. So pressure is known to me, pressure at inlet, pressure at outlet is known to me. I will put the standard value of density, I will find the values of velocity. So this whole loss across this valve will come out to be 5660 foot-pound. So this will be my final answer, and this was what is required. That was, if the flow through the valve occurs in a horizontal plane, determine the loss in available energy across the valve. So this is the loss due to the viscous effects, because we are not considering the loss due to the mechanical effects, because there is no such rotational components inside this valve. So the only loss that will be occurring due to the viscous effects. So hope this was clear. So now we have a problem. In this case, water is supplied at 150 cubic feet per second. So this is our volumetric flow rate Q, which is already given, I suppose. That is Q is equal to 150 cubic feet per second, and 60 psi to a hydraulic turbine through a 3 feet inside diameter inlet pipe as indicated in the figure this. So this is our section 1 as already mentioned in the diagram. P1 is the pressure at section 1, the flow rate is already given, and the diameter of the pipe at section 1 is already given. The turbine discharge pipe has a 4 feet inside diameter. This is the discharge pipe. The static pressure at section 2, 10 feet below the turbine inlet, is 10-inch mercury vacuum. This is the negative pressure in terms of inches of mercury. So this is negative. Its value will be negative. If the turbine develops 2500 horsepower, determine the power lost between section 1 and section 2. So we are going to find this term, that is the power lost when the water comes from section 1, strikes the turbine, and then moved on to the section 2. The total height between section 1 and section 2 is given as 10 feet. So now we are going to write equation in terms of our HL, that is the power loss that we are going to find. So let's write the equation, that is our HL will be equal to P1 over rho G plus V1 square divided by 2G plus Z1, and this is minus pressure at section 2 divided by rho G plus V2 square divided by 2G plus Z2, and minus this HS. This is the shaft work head. And in this case the work is done on the shaft, means our system is doing work on the shaft. So the system is losing energy. That's why I have put the negative sign here, because it is a turbine, and as you remember in turbine's case we will use a negative sign to indicate that the fluid is doing work on the turbine. So what we know in this equation is the pressure P1, our velocity V1 is unknown. We know the height at section 1, that is 10 feet. The pressure at P2 is given in terms of inches of mercury, so we will have to convert this, but it is given. V2 needs to be found out, and Z2 is at 0. So Z2 will be equated to 0, and our shaft work head can be written in terms of rate of work transfer per mass flow rate. So this term, this HS, can be written in terms of W dot over rho GQ. So this rho G is for gamma and this Q is for volumetric flow rate. We can write it like this as we mentioned when we were comparing the Bernoulli and the energy equation. So we wrote this term. You can revisit those slides. So we can write our shaft work head as this. So if the turbine develops 2500 horsepower, so this is the horsepowers that the turbine is developing. So here we will put the value 2500 horsepower. So now we are going to find our velocities. We will find our velocities, and we will first convert our pressure at P2 into pound per feet square. So 1 inch of mercury pressure is equal to 70.73 pound per square feet pressure. So to convert 10 inches of mercury into this, we get P2. I will write here P2 is equal to 708 pound per square feet, and this is negative pressure because vacuum is mentioned, so by vacuum it means negative pressure. So that's how we will convert our P2 to pound per square feet. Now we will find our values, that is V1 square and V2 square. So for velocity we will use our volumetric flow rate, that is Q is equal to A1 V1. For our velocity V1 we will put our area as pi by 4 D1 square. So we know the diameter at D1 is 3 feet. So we can find this area. We know the volumetric flow rate, that is given in cubic feet per second. So we can find our V1. Similarly, we will use the same for V2. Here we will put our area is pi by 4 D2 square. So here our D2 is 4 feet. So we can also find our V2. So these are the equations that are going to be used to find V1 and V2, and the rest of the values we know. We will just make sure that all the length dimensions are in feet. So wherever you see inches, you will need to convert them into feet, like here in P1. So we will have to convert this, that is pound per square inch. So we will need to convert into pound per square feet. So you will need to convert this P1. So please convert this and then put it into this equation. So now we know all the values. We know our P1, we know our V1, we know our Z1, our P2, V2 and Z2 is equated to 0. Our shaft work head is negative due to the turbine, and that is equated to this term. W dot is the rate of power, that is given as 2500 horsepower. So we'll put 2500 horsepower here, the density of water here, the gravitational acceleration here, and the volumetric flow rate here. So we will get our value for shaft work head. So by putting all these values and solving it for our losses, we will get our losses equal to 301 horsepower. So in this case, we were required to find these losses, and this will be our final answer. This will be our final answer in horsepower. So in this case, we were given a turbine and all the values were given almost. What we needed to do was to convert some values, that was our pressure at point 2, and our velocities were need to be found out with the help of our flow rate, that is our flow rate, and the rest was given. One assumption that we made is that at section 2 height is equal to 0. So we took Z2 here is equal to 0 because this was our reference for this scenario. So that's why Z2 was equal to 0. The rest of the values were easy, just need to be put into this equation. So just make sure, if you are going to solve this equation, just make sure that all the values for the lengths are in feet, just as I mentioned for this pressure, that you need to convert it into pound per square feet to solve this problem, and our velocities will also be in terms of foot per second. So make sure the dimension homogeneity is in place, and then just put the values and solve it for the losses, that is our HL. So I hope this was clear.